Okay, and so again, so in fact, already right in the title, we've already got a fair bit of jargon going, which is non-exchangeable coalescent arising in phylogenetics. And so to motivate that title, I mean, the sort of neutral models that Bill was just talking about are examples of exchangeable processes. This is the idea that sort of everyone is equally good as everyone else. And sort of elaborate on that as I go along, but that's sort of a very nice modeling assumption that doesn't necessarily hold up very well biologically, and so we're trying to move beyond that. There's all these sort of things, it's harder than you think. So what I'm really going to do is present a model, and I kind of jumped on this opportunity because there wouldn't be many people here to talk about work in progress. And so I'm going to show you sort of a collection of results that are slowly accumulating into a full picture, but maybe the full picture isn't there yet. So just to talk about this work, as I said, it's being done with colleagues of mine. Guillaume and Nicolas are both bioinformatics, and Emily and I are more sort of at the mathematical end of the spectrum, though we're both sort of pretty much actively interested in modeling and biology. And the kind of questions that we're interested in getting at are patterns of biodiversity, and really kind of moving from pattern, which is what we can observe, to process, and trying to ask if we can make the link between sort of observed pattern, process, and then the primary sort of data that we often have to work with is phylogenetic data. So as we, sort of what we do, most of us do in the field, is sort of one person needs to sample a whole bunch of stuff. Maybe you bin it into OTUs, and then you run beasts and all that machinery, and you generate a tree. And then when you the question we're kind of interested in, okay, well, what does that tree actually tell us about the underlying processes? And sort of run up the side here, I mean, sort of showing sort of diversity gradients across the oceans and across the landmass, and then an image of a phylogenetic tree. And so there's sort of various things that can go into creating pattern. I mean, first one is sort of indicating about, we've got this gradient along sort of latitude, the amount of biodiversity, ocean currents and so forth shape biodiversity. And so these are sort of more external factors, but the kind of questions that I want to talk about today actually are more the internal factors, which have to do with selection and essentially sort of different birth rates. And just sort of to give a bit of a historical background, sort of talk about is that the sort of archetypal model that most of us are using when we look at phylogenetics, it's sitting underneath everything as the prior in things like yeast. It's also the primary tool that's used in most forms of phylogenetic analysis, is the Yule process. And so this goes back to very classic work by Yule, which he basically wanted to simply ask the question, why are there as many species as there are? How are they, sort of, what is the distribution into clades? And sort of in the sort of standard sort of mathematical null model approach, he started off with what would possibly be the simplest model you could think of, which was a pure birth process. So essentially, you start off with a single ancestor or a finite number of ancestors, and imagine that there's a rate, a random rate through time, probability lambda per unit time of producing an offspring. And when that event happens, is splitting. So normally we think about pure birth processes as being talking about individuals, but Yule is really thinking about it as species, as being sort of the atomic units here. So a species persists for a certain amount of time, and then at a certain rate it splits off and gives rise to a new species. And in the Yule model there's no death, so basically everything kind of continues on forever. And it actually does remarkably well, the sort of data that Yule's looking at. I mean, when you look here, I've just got here is a table right out of Yule's paper. I have David Alvis's paper talking about Yule's paper. But when you look at sort of, he basically went through it, he broke up in this case, the number of snakes by genus, and then looked at the number of species in each genus to sort of get a frequency count. And the fit is remarkably good, actually, when you look at this, between a model which is fit with a single parameter, this branching rate, and the actual genus numbers. I've never gotten a match that good with data in my career. And so for a long time, this story kind of seemed like it was just over. I mean, Yule had done it, it worked beautifully, we're done. But of course, in the modern age of phylogenetics, we're starting to revisit these questions, and there's a lot more to it than that. And I mean, just to sort of start off with a very, very, very basic sort of picture, we have here sort of on your right and your left, here's a simulation from a Yule process, and here's the actual phylogenetic tree which arises out of the botulism bacteria. And what you start to look is that sort of, while Yule's process gets generally gets the numbers right, as I showed in the previous slide, I'm hoping that you should be able to eyeball these and say these trees don't really look the same as each other. And the sort of, here it's kind of balanced, sort of essentially there's a lot of symmetry in this tree as I sort of look at each side of it. Here we kind of got this long trunk structure and sort of spreading off in one direction. And so, one of the next steps I think sort of we'll talk about after this step is we started to see that, okay, maybe it might get sort of rough numbers right, but it's definitely getting the topology wrong. And we'd like to think that the topology of the tree, the branch lengths, the structure, really is carrying a lot of information. And so we need then is a model which is going to capture that structure properly. Now, before I talk more about the modeling, let me just sort of talk about two summary statistics, which I'm going to be interested in later on. And they, for me, sort of capture what I was talking about. I said about the balance, our intuitive notion of balance, and also sort of balance both in the symmetry left and right, or sort of how much the tree is like sort of one side versus the other, and then sort of the relative lengths of the branches. So when I talk about, so just to sort of be clear, when I sort of this black down here for just a second, I would hope that we would all agree that that's a pretty balanced looking tree. And that's sort of, these two extremes of balance are sort of right here and here, right? And so, one thing that sort of, David Aldous in a great paper in 1996, basically wanted to sort of capture this idea of balance in a more formal way. I don't want to go into the details of his mathematical model because it's quite complicated, and by his own words, was neither mathematically nor biologically motivated. Right in the paper. But what he did basically is he introduced a single parameter class of models, which he called beta splitting trees, with the property that basically at the two extremes, when beta is equal to -2, yeah, that's right. So which one? Yeah. -2 is sort of extremely unbalanced, which means sort of this tree here, which kind of like everything is shooting off to one side. And at the opposite extreme, as beta goes to infinity, you get a perfectly balanced tree, like my tree over here. And so basically, he wanted to sort of capture the entire spectrum of possible balances. Those are the two extremes of the model, and sort of all the betas in between kind of interpolate between those two extremes of balance. And what you find is, the way that his model is designed and calibrated, beta is equal to 0 gives you the Yule process, which I talked about a moment ago.
So the Yule process isn't perfectly balanced?
No, it's not perfectly balanced, actually. The biggest sort of this, it's awfully close, but it's not perfectly balanced.
Mm-hmm.
And what was interesting is sort of when you find again, sort of Yule gives you exactly 0, but then a good 10 years after Aldous published this paper, someone actually did sort of the obvious thing, which is they took real trees coming from real species and asked, well, what's the beta looks like on real trees? And they found that pretty much exclusively beta was negative. So basically, Yule trees are too balanced, kind of like the intuition I showed in the previous slide, to really reflect real diversity. At the same time, another statistic, which is really kind of interesting, is the gamma statistic. And what it does is it wants to tell us a little bit about what the relative branch length is going back in time. And so, again, there's a formula for this. It's, in fact, possibly even more contrived than the beta statistic, because it was essentially just kludged together to give a statistic such that it was, in an appropriate limit, for the Yule tree, the relative branch lengths were Gaussian distributed about 0. And so the idea basically is it's a summary statistic which captures that when gamma is positive, you tend to have more of your nodes closer to the tips. You have very short branches near the present, and they get longer going into the past, which is the signature of a Kingman coalescent, standard model in genetics. And when gamma is negative, what you see is that they're sort of more evenly spread, and there's a lot more branching closer to the root. And again, sort of, if the Yule model is sort of one of the standard models that people are using in this field, the Kingman coalescent is the other standard model that people are generally using as the background of phylogenetics. And once again, we sort of see for our crucial statistic, we have the Kingman coalescent that gives us a positive value of gamma, Yule process gives us a 0 value of gamma, and the actual trees are giving you a negative gamma. In other words, edit this out later. we have these sort of two statistics, which I think are sort of very natural statistics to look at, which are telling us something, which are really capturing essential topological properties of this tree. And the models that we use, sort of the go-to models in population genetics and community ecology, basically fail to capture the real biology of these two summer statistics here. And so, to some extent, the work I want to talk about today was really an attempt to sort of start to come up with a model, unlike Aldous' model, one that was both mathematically and biologically motivated, in order to try and get something which had the same degree of freedom moving across these trees. If you were building a better prior. And so the model we want to do is, because we're all sort of statisticians and probabilists in our group, is always we want a probabilistic model. And we want to be able to generate patterns based on mechanism that are going to look like the things we see in nature. And it's kind of always the goal, is we'd like to be able to infer these things, be able to reject models. And it's kind of, I guess, one of our major motivations in this group is to sort of start building mechanistic models that we can then throw against phylogenetic trees to try and say something about process. And the type of models we've been playing with have been what I call lineage-based models and individual-based models. I'm trying to talk about something we'll try and link to together today, but let me just start by talking about what I mean by each of those. So the lineage-based models are the models like Yule's. What that means is that the atomic unit of this model is the species as a whole, not individuals on the species. And typically, so we're imagining this we have various processes, and the simplest version we're getting a tree is we can have the birth of a new species, a speciation event, and we can have an extinction event, which causes the loss of a species. And there are a wide variety of complications of these models. They've really been exploding a lot. There's probably been dozens of papers written in the last 10 years, just having variations on this theme, where we take those rates and we say, well, they might depend on time, or they might depend on existing species diversity, traits, et cetera, et cetera. I've written some papers like this, and I've written some papers, lots of people have written papers like this. Now, the advantage of these lineage-based models is that they tend to be quite tractable. We can use a lot of classical theory from branching processes or classical theory of chemical coalescent to actually sort of fit things like do maximum likelihood estimators of the tree, and they start to be able to do useful things. I mean, my own work in the area, sort of up there at Moreland, Parsons, and Plotkin, was we basically looked at a simple individual-based model, sort of lineage-based model, and allowed time-varying rates, and were able, with that, to get convincingly good estimates of extinction and speciation rates for the whales and dolphins. And that even told an interesting biological story, and that's just based on simply using branch lengths and nothing more. So these things are great, they're tractable, so you can do stuff with them, but I guess they don't really give you a whole lot of insight or what's happening at the level of individuals. They don't tie down to individuals. You can't use measurements about individuals to calibrate these models. And so as a result, they don't really make predictions at the level of groups of individuals. They only really make predictions at the level of species, and they tend to cram, sort of really lose a lot of potential information and calibration, and they tend to also be really phenomenological, to the extent that I would argue that, one of the shortcomings of my own work in this area, paper above, essentially the model is so general you can pretty much fit anything with it, with the right parameters. That's a good model. I guess it's coming from a statistical background, it's a bad model. Now, at the other extreme, sort of what we see a lot of in the stochastic end of biological modeling are individual-based models. Bill sort of, I will not elaborate about this, but Bill's talk about the idea of neutral models have become very popular and very widely debated amongst ecologists, population geneticists, and so forth. It's interesting, the population geneticists seem to accept them pretty well as a null model. They're a null model which we're trying to usefully reject and try and build upon. In the ecology community, it's sort of less favorably regarded, I might say, but really quite useful. But they're individual-based, they're mechanistic, and all. But the problem is that they're really difficult to do much with once you try and step away from the neutral hypothesis. There's always simulation, but if you're interested in doing analytical work, if you're interested in doing inference work and so forth, it just gets harder and harder. And the other thing is that, I mean, for various reasons, I mean, neutral models are not completely satisfactory. We know there is selection. And the last thing, as I mentioned previously, is that all of these neutral models, the underlying genealogical structure of the underlying trees, are basically Kingman trees. There might be complications, you have multiple subcommunities, but they are essentially Kingman trees. And as a result, they're not getting gamma and beta right. And so we like these because they're individual based, we measure individuals, we can quantify them, we can calibrate them, but they don't do all the things that we want to do. What I want to try and do is talk about what we set as our goal is, could we come up with something which was individual based, biologically motivated, based on a mechanism. It's going to be a simple mechanism, but it's a mechanism. And hopefully it will be mathematically tractable, and if we're really, really lucky, we might even be able to get the beta and the gamma right. And so our point of departure was to sort of ask, what can we, so we want to have sort of a very simple model of fitness effects. The whole point of the neutral model is there are no fitness effects. Species are essentially labels. We can just interchange two individuals. They have the same ecological function, the same competitivity with each other. That limits to sort of, and whenever I say fitness, what I'm talking about is expected lifetime reproductive success. And the definition of a neutral model is two individuals have this, every two sampled individuals have the same expected lifetime reproductive success. So we sort of went, let's go to the opposite extreme of that and go with an interesting hypothesis, which is sort of occurred again and again in the ecology literature, which is what's called the Red Queen hypothesis. In the sense that you're running to stand still. And so what we want to do is translate to that. It's basically saying that we're always in a situation where you either innovate or die. And so what we're going to imagine is a process by which speciation events correspond to key innovations. Essentially, each time there's a speciation, again, if you will, sort of, it's an equally unrealistic model, the Kingman model, because rather than saying everyone is the same, we're going to say that everyone basically has a substantial fitness advantage on birth over all the people who exist already because they've managed to innovate. They've managed to find some kind of ecological innovation which allows them a release from competition. Again, it's also a toy model, but it's a toy model that has selection built right in at the bottom, and we'll be able to see that it's sort of at least partially mathematically tractable in a way that's useful. So let me start by underlying just sort of the underlying individual-based model, because then this is going to pass later on to a lineage-based model through a mathematically rigorous limit process. So again, to get to this idea that we're going to start off, we have not a finite and fixed population like Bill's talking about with the neutral models, but we still have a carrying capacity in these models. Okay, so in this case, we have sort of a stochastic logistic process, by which I mean there's a carrying capacity K, which is giving us sort of the relative order of magnitude of the population size. If you're much above K, you're going to be experiencing sort of increased mortality. If you're much below K, you're going to see an uplift. So this is sort of, K is giving us, is at least proportional to our equilibrium level about which there'll be fluctuations. And so imagine that individuals have an intrinsic birth rate lambda and an intrinsic mortality rate mu. But in addition to that, they experience competition. And competition is going to be resource mediated. And there are two coefficients in this model, basically C and D. C is competition with like, so intra-species competition coefficient, and D is competition between species. It's interspecific competition. And what we're going to do to get this idea of the Red Queen effect is to say that you're always competing with like, that just, you can't get around that. But in terms of competition with other species, is when you arrive, you compete with your descendants because they carry the same innovations you do, but you don't compete with your ancestors because you've managed to sort of release yourself ecologically from your ancestors. That's our model. We can relax both of those a little bit, but sort of at the cost of more parameters and greater difficulty in the analysis. So it's kind of want to stick with this really toy model. And carrying capacity K is going to vanish out eventually because I'm going to be interested in when we pass through the infinite carrying capacity limit. So, as I said, sort of apologies for the
No,
jargon
that's-
here.
that's
I'll
good.
walk through what this actually means. So now the first thing is just for language, because level-based processes have become really hip in population genetics in the last 20 years since Donald and Kurtz. So what we're going to do is for our use, just as you sort of a mental utility object, we're going to imagine that the species are actually levels. So whoever is the most recent species sits at the bottom level, and that is because you're only competing with people who are below you and not above you. So the most recent species is at the bottom level, next most recent species level above that. So we have these levels. And we're going to track species by simply saying that they have a level, and that level is going to be changing through time. It goes up when sort of something new comes along, it goes down if something more recent goes extinct. And so the first thing what we do is we can basically pass to a very simple deterministic limit in the system. And the way it was contrived was if we rescale from, so xi right now is the number of individuals of species that are at level I. And again, I'll continue to use level because we're going to basically, in this model, the species is kind of like an arbitrary label, but your level determines your competition strength. So we're basically going to sort of just track the number of individuals at each level. So basically what we're doing is we're rescaling, going from a species numerical abundance to a density. So that's what taking the K inverse is. And then passing to a large population limit. So good model probably for bacteria and viruses, not so great for the at risk of extinction Kirtland's world over 200 individuals. You know, and so what happens is that when we pass the limit, we get a set of equations. They're essentially just a simple logical Volterra system of equations, where again you're seeing sort of this intrinsic birth rate, self-competition is reducing your rate, and sort of competition with your ancestors further reduces your birth rate, and that's all its per capita rate. And what's nice about this model is actually originally we discovered after we'd done this was actually Tillman had considered the same model about 20 years ago in a paper for looking at coexistence. And it has some really nice properties, and one of them is that basically we get two parameters, so two numbers kappa and alpha, and then as t goes to infinity, this thing settles down to basically you have all the species are present in essentially geometrically diminishing abundances. And this sort of alpha basically is then the sort of the scaling factor here. So the most common species takes up about kappa of the environment, and then everything else is sort of being geometrically reduced down by a factor of alpha. And so in other words, what this is telling us is obviously the younger species are really going to be the most abundant ones because they're not experiencing as much competition, but kind of the opposite extreme of a lot of models. Sort of instead of competitive exclusion, everyone gets to be present, but just in ever diminishing quantities. And so that's sort of describing right now the ecological process and the limit. And so what we can also do is we want to think about more than just births and deaths. Obviously, we're interested in models of phylogenetics. We need to have species in here as well. And so we imagine that there is a probability epsilon k, depends on population size, carrying capacity, that an individual carries a mutation, and that is not merely any old mutation. That's a mutation which is giving it a significant selective advantage. This is a release mutation. And so one of the things that this is an assumption made for mathematical reasons here about sort of the size that this epsilon k can be, but I think it's also biologically motivated. We know kind of the sort of rough heuristic in population genetics is you have one mutation per base pair per generation. So what we usually say is we have a basically mutation rate scales more or less like 1 on n, where n is the effective population size. So if you have a population 10 to the 9, your mutation rate is 1 to the 10 to the 9. And so that's sort of your overall mutation rate. Here what we're interested, so if you will sort of K is taking the place of the effective population size here. And the first thing I want to remark sort of is that we're not going to ever get as big as 1 on K. Again, we wouldn't expect, because we're talking about mutations that really can convey a selective benefit. We don't expect them to be as common as all mutations. We expect them to be a lot rarer. And so that's basically, that's the biological justification for sort of this lower mutation rate limit. The mathematical reasons for doing the two extremes our ln k is about the time the system takes to approach equilibrium. And so what we want to do is we want to have a mutation rate low enough that we're not going to see what's called Hill-Robertson effect. We're not going to have competition between two. Essentially, we expect innovations are rare enough that we're not going to see a whole bunch of them dueling it out, and rather we see them as more or less one at a time. They'll come through and sweep. So this is we're basically working in the assumption that we see a series of sweeps rather than sort of a whole bunch of competition down below. The other extreme, basically, this exponential limit is that it's entirely for mathematical reasons, and sort of that's giving you sort of mutations have to happen often enough that everything doesn't go extinct by a rare event before the next mutation.
So, sorry, where you're talking about getting sweeps, is that assuming that you're sort of starting with one species to start with?
So we'll mention, sort of, I said, I should be clarified, when I talk about a sweep here in this case, it's not actually replacing everything. What's happening is an individual is arising, and then it's either going extinct rapidly, or when I say sweep, it basically manages to escape initial extinction, and then is able to rise up to this sort of fraction.
Where it's predominating in the population.
It's exactly, so in this case, so it's always a partial sweep in the model, because coexistence, like our model sort of allows for coexistence of many species. The idea is that a sweep basically means growing up to macroscopic level and being at this new level where you basically get to really sort of dominate the community without excluding everything else. And then when something else sweeps, you continue to exist, but you now get a smaller piece of the pie. And so the idea is that under this mutational limit, what we can do is rescale time and pass to a large population limit where all of the structure almost collapses out of everything. What we're left with is our individual model has given rise to a lineage-based model. Where basically now each level now actually is in itself sort of, with all the species in it, it basically becomes a species. And we can basically now look at the whole thing as just the levels themselves as being a process, because all of the population dynamics kind of get collapsed into the model in the large population limit. And so what this is saying here, all this jargon, which just disappeared again. Is that instead of having to track each individual population, now what's happening is that on the new time scale, which is sort of the mutational time scale, it's like an effect, is that we now have a process which basically looks like everything is at their equilibrium abundance, and then events come along at a rate, rho, written up there, which is a speciation, which means that sort of everyone gets pushed up one level, and their abundances go down accordingly.
This assumption that K can tend to infinity. Is that so? K you said was like an effective population size.
That's right.
So you're suggesting that the effect, with bacteria, then the effective population size is huge.
Yeah.
I wonder if that's actually true.
Depends on the species, to be honest. I mean, again, when I say a lot of them in sort of machinery of population genetics, we know, we take what was the phrase I come over use, the unreasonable effectiveness of mathematics, right? So I mean, all the population genetics theory, Kingdom coalescence, rank distributions, are all created in an infinite population limit. But what it turns out is that for practical purposes, I shouldn't maybe say this on camera, infinity is 50, for most of these models. And really what it kind of turns out is that what's not really important is n going to infinity, it's more that it's the relative size of things, which is why that sort of 1 on n mutation rate is so important, is that we want to make sure that we've got the relative size of rates stay the same as we pass the limit. And the idea is sort of, and passing the limit, what ends up happening is we lose a lot of structure, keep the essentials, and something which is attractive one still works really damn well. And so to draw this picture, what it looks like in terms of our forward time process, again, as we have these levels, we start off, so in this case we have us start off with an initial community of 5 species. Time passes, and an individual in species at level 4 gives rise to a new mutational type. So we show that by so we have a line here which connects that now down. This is now the descendant species of species 4. It's now the most abundant species. everything else has gotten pushed up a level. And so there, and sort of, again, we're only just in the level dynamics at this point in the limit, but what we're seeing here basically is that each one going up there is becoming less and less abundant. As a result, I mean, sort of one thing that's also telling you is that although here we see a speciation event at level 4, the higher you go up in the level, obviously the less likely you are to be the ancestor of the new innovation, because essentially there's just fewer and fewer of you to produce new mutants. And so one of the things useful about this is that this model does allow an infinite number of species in theory, but in practice, they're never going to really play a part of the role. They're kind of just pushed off there, and they do their thing up there, which basically just mostly means moving farther off to infinity. All the species down below are really the ones who are evolved and adapted. And you know, what we want to do, the Richardson tree, is move from a picture forward in time to move a picture backwards in time. And the backward in time picture looks like basically the same, which is that we run along through time here. We have our sampled species, and then at rate rho, remember I said it was our rate of speciations, we now see coalescence events. And at a coalescence event, our species, who is the most recent, because they're the one who had to have been born in that event by the definition of the levels, looks up above it and picks an ancestor. And what I said basically is that the abundance of these things are declining sort of with this geometric factor alpha. So what it does basically is it chooses a number from a geometric distribution with parameter alpha, and that's who's going to be his ancestor. And it merges with that, creating a new line, and everyone else shifts down. And sort of because, again, forward in time, everyone shifts up to accommodate now, backward in time, we're shifting down to below. And so we started referring to this as the look-up, shift-down coalescent as a result. That got coined by accident, and now sort of seems to have made its way into the manuscript that we're working on. So I said, so to sum up what I've just been saying in words, is we have, once we pass to coalescence time, which is this mutational every scale time rate, we have this constant rate of speciation, rho. And just to tease it apart for you, basically 1 minus mu over lambda is the probability that a species manages to escape an early extinction and does manage to sweep. And then kappa, basic, over 1 minus alpha is the number of individuals who, essentially is proximate to the number of individuals who are able to produce a new offspring. So basically we're saying it's an individual-based process. Each individual has a certain probability of giving rise to mutation, and we thin those mutations by the ones that are actually going to sweep, and that gives us the rate of sweep events. And again, the ancestor basically, as I said, is geometrically distributed with parameter alpha, where alpha, just to remind you, was 1 minus C over D. And so basically, alpha is giving you the relative strength of competition between self-competition and competition with your descendants. So if you will, sort of, when alpha is 0, you're basically almost, essentially you have almost no competition with yourself. When alpha tends toward 1, which is its largest possible value, you basically are competing with your like pretty much equally the same as you're competing with ancestral. And again, the way we represent this is by the sort of level process by which sort of forward in time you're shifting up a level, and there's a new level being put down below you. Backward in time, you shift down a level, and every once in a while something looks up and merges to find an ancestor.
Remind me what alpha is again, sorry?
Yeah, so alpha was 1 minus C over D. So C was your strength of interspecific competition, D was your intraspecific, and D was your level of interspecific competition. So basically alpha is, as I said, basically alpha is really measuring the relative amount you compete with yourself versus other species. And the closer alpha is to 1, the more equal your competition between self and other is. As alpha tends to 0, it's the more you're more strongly competing with other species and less with your own type.
So how does it tie? So it looks to me that it's like it's a lineage type of model now. That it's not. It's lost the individual.
But that's what it passing to the limit, right? So what we've done is we posed everything at the level of individuals, and then said that happily all of that structure of individuals, rigorously mathematically, sort of with measurable properties that they have. I mean, was these sort of, and we can sort of sit down and you can do a competition essay, you can figure out how well they compete against each other, how well they compete against other species. So all of those individual-based properties are still sitting underneath the model, but they've now been basically collapsed down into two parameters. And sort of this rho, which is the rate of speciation events, actually the rate of successful speciation events, and alpha, which is this, again, this proxy for competition, which is also basically telling you sort of who your ancestor was based on a geometric law. Let me just, again, as I said, sort of my caveat at the beginning was this is still work in progress, so we're still collecting a whole bunch of results about this. So I wanted to just sort of run you through some of the results that we have got. So the first one is just a very simple way. We like to kind of know what the level process looks like through time. Like if I have an individual, can I say what level they were at a time in the past? And it actually turns out to be a very simple model. It collapses down to just a pure death and immigration process. By which I mean that you basically, if you imagine my level right now is L, I can think of L as being numbered, and when L goes down by 1, that's a death. And so basically you kind of have a situation where every row, every time there's a speciation event, your level's going down, 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 because sort of the bottom plane has been taken out, and you're getting close. And then you finally hit the bottom, but now that means you're the most recent species, and then you jump up, and that's an immigration model. So basically you have all this theory that already exists for death and immigration processes. We want to analyze the individual level process. And that allows us to do things which I don't want to write down the formulas for, but we can explicitly write down a likelihood of a tree if we know sort of tracking all the levels of individuals going through time. And what that's useful for basically is our likelihood now is basically, in fact, what we can do in fact with that tree is we can take a step further and we can actually toss out rho also as a parameter, because rho is just giving us the spacing and time of events, but if we're not concerned about that for the moment, we're just concerned about the actual topology, then it turns out that alpha is actually parameter enough to describe the topology of the tree, the likelihood. And what we need, sort of, if we want to fit alpha, then is basically all the lineage information. Sort of who was at what level at what time in the past. Now, the problem with this is that it's all great, except the fact that it was really super computationally intensive, and we had some nice mathematical results that got us this far, and then it was like, okay, let's simulate this process and try and compute the likelihood of an actual tree. And when we had more than a tiny, tiny tree, this just got out of hand. And the reason for that, as I said, is that this likelihood depended explicitly on what level you were at. But the idea sort of is that those levels, if you think about it, they're constantly changing. They're going down, 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 shooting up, down, down, down. So you don't want to track all that information in a simulation. So what we did instead was, actually Guillaume came up with this very clever idea, was that we didn't actually need to track all the levels, it turned out. I'll sort of summarize this, because I want to show you simulation results later, just to explain how we got there and how we turned this into a computational tractable model. And so what we do is instead of tracking what level you're on, we track how many times you've merged with someone else since the last time you were the most recent species. Remember, say you're going down, 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 you're not bottom species, but then you merge back with your ancestors somewhere up above, go down, down, down. So essentially, so in this case, we look at sort of this top line here. At the beginning, it hasn't merged with anyone yet. Then it merges with its first species here, and it gets a weight of 1. Comes down a bit, merges with the second line down here, gets a weight of 2, down, 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 merges with a third time, gets to 3, comes down to the most ancestral species, in which case its clock gets reset, and it becomes a 1, and it just jumps up to some ancestor back in time and becomes a 1 and again its weight. Now the reason that turns out to be useful and why it's so clever is that instead of having to track all this lineage through time data that we had before, it turns out all we need to do is track weights, and we only need to, whereas lineages can go, so your level can go up to infinity, come down, go all over the place. If you have n species, your weight can be at most n in your sample. And so I'll sort of again just jump through quickly. But it turns out our next sort of mathematical result on this is that we can just describe a weight process, and we'll leave them out here, but you can explicitly write down a Markov process, which is your weight process, which is very easy to simulate, which basically your weight can either go to up by 1 or it can get reset to 1, and you can write those down explicitly. What it turns out basically is that essentially what we can do is say that if we have a vector of weights, and typically we're going to start with everyone as weight 1 because we haven't seen any mergers yet, so everyone hasn't merged yet. And then we construct a series of independent geometric random variables with parameters alpha to these powers of the weights. And if you sort of condition those on always being distinct, then what it tells you is it sort of gives you this nice recipe for actually reconstructing all of the levels probabilistically from just knowing the weights, which turned this from an intractable computational problem of having to track all these levels to only having to track, if you have n individuals in your sample, you need to know n weights, and that's all the information you need to reconstruct all the levels for at least the purposes of understanding what happens in the process. The technical, but I just wanted to sort of I just find it so clever when he came up with this that I wanted to share that. And what that does again is basically gives us now a very quick simulation method, for example, for generating the trees, because we sort of we generate our weights through our weight process, that generates our level process, and that turns into a tree. And that also leads us to being able to sort of write down the likelihood in an equally computationally tractable way. And the reason that I want to get to this simulation is because I kind of started off here, we're talking about these statistics gamma and beta, which sort of seem to have just exited stage left, and here they come back again. And the reason is because what's lovely about this is that we get what we wanted to get in the first place, at least with the beta statistic, was a biologically and mathematically motivated way of getting these range of balances of trees. And so first of all, you notice that we take alpha really close to 0, we're getting sort of the highly unbalanced tree that I talked about before, the kind of caterpillar tree that we tend to see in things like viral evolution. Sort of obvious why we call it a caterpillar tree, I think. And as alpha gets bigger, we get things that are looking more and more balanced and more like a Yule tree. And as alpha gets bigger still, we get things that are starting to have lots of branches down at the tips and lots of longer branches and really balanced. And what we see again, sort of as we start to run through our alpha, we're able to capture, what we're doing here is taking all those statistics. So we're saying that we're going to run a simulation of our process, generate a tree. Then we're going to find the best fit beta according to Aldois's beta splitting trees, and that gives us our beta statistic. And what the slide is showing us is we're getting a really nice, we're getting down from -2, which is the extremely unbalanced range, right up to around 0, which is what we saw was sort of, remember, was the Yule tree, and it was the 0 to -2 range that was the biologically relevant range for the betas. The other thing just to notice is that I was sort of emphasizing the fact that if we turned up alpha, ratcheted it up and up, we were getting something that was looking more and more sort of spread out, lots of stuff near the bottom, not so much near the top, and lots of balance. And if you actually look at sort of here, I'm plotting the ratio of coalescence times to the time the most common ancestor, which is giving you a nice sort of measure of how much something looks like a Kingman coalescent. And what you see is as we go from as we sort of ratchet up our alpha from 0 to 1, we're basically getting closer and closer to a Kingman coalescent. So it's nice basically because we have essentially our class of models now, it looks like, and we can mathematically prove that. In the extreme of alpha, we basically just recapture the Kingman coalescent, whereas at the extreme of alpha is equal to 0, we capture the perfectly unbalanced tree. So what we have got now is a one-parameter family of things that can interpolate between Kingman coalescent, the neutral model, which we said wasn't satisfactory, and the completely unbalanced tree, which we said, which is also got unsatisfactory, but basically we're allowing sort of to capture that whole range of processes in between. And this is really appealing to us now because what it means is that we have sort of a model, we have a mechanism behind it, which is this idea of self versus other competition, which interpolates across the biologically realistic range of balances of these, captures in one end sort of our null model, and then basically now we have likelihood methods, we have MCMC methods, we can effectively reject the model, we can reject our null in favor of a value of alpha, which is a biologically meaningful concept, which sort of, and again, get that range. Just to show, we haven't unfortunately had a chance to apply this to real trees yet, but just to show how that sort of we're getting sort of nice sensible results from MCMC methods, is when we start by taking the pure caterpillar tree, and we estimate that, we get sort of a Bayesian posterior distribution, which is strongly focused at 0 and sort of quickly diminishing from there. So we're able to quite capture the strong imbalance of this tree. A less extreme but still highly imbalanced tree, sort of we can safely reject both completely unbalanced and neutral in favor of getting. And in a balanced tree, again, we sort of we quite recently capture values of alpha which are closer and closer to 1. Again, work in progress. We want to start applying this to biological trees at the moment. But at the very least, what we can say, we've got a simple model with biologically meaningful, individually based underlying parameters which can be measured, either sort of by inference from a tree or by an assay in the lab. So we're making this connection between the lineage-based process and the individual-based process, which is based on sort of, again, a mechanism which we can either accept or reject, which is that this idea of a sequence of ecological innovations leading to a red queen effect. We have a nice representation of it, which allows us to very quickly simulate the process and very quickly do inference on the process. And we have this nice property that sort of we capture the biologically meaningful ranges of balances. We capture sort of as a submodel the Kingman coalescent is a submodel which we can then sort of reject or accept. And I think I feel like we're on something kind of, at least I think we're heading in the right direction here, and hopefully in time we'll be able to add this sort of overlaying mutations to be able to do sampling formulas and so forth. But at least for the moment, sort of it's a start. So with that, thank you very much for listening. Thanks to Bill for the invitation to be here, and to the Université for having me. And finally, well, sort of thanks to my group, I'll also put a plug in for them, stochastic models for the inference of life evolution, because the French love acronyms. That's our group in Paris doing this work. So are there any other questions?
So can you make a connection to the earlier, say, frame that you exposed on how this helps to understand or to model distribution of species in the global landscape and so on?
Yeah, so basically, I guess I will sort of say right now, in the absolute global perspective, we don't have anything, right? Because in the global, there's all kinds of other sort of, in our model here, we're really looking at sort of really endogenous effects of competition. In the global, there are different niches and so forth. It's more complicated. But at least what we have sort of is a model which, unlike the sort of standard tools on the shelf right now, has selection in it, right? And so we have a tractable thing in which we can sort of measure the strength of selection. And that selection, I mean, because we're mathematicians thinking about this, rather than wanting to think about really specific, like this is better in this niche than that is, we'd like this capture to say that this, for whatever reason, this one has a higher birth rate than the other one. So basically, we'll abstract out all of that real structure in favor of just a fitness effect. But then sort of, I mean, if you want sort of one way, for example, to connect it with species is that I talked a lot about ecological innovations, but I mean, one of the ways you can also interpret this model equally well is as an island model, right? Where sort of, if you're only competing with your descendants and not your ancestors, it's because maybe you just colonized a new island, and therefore you're only competing with your descendants because you've left the island but not your ancestor, and so everyone needs to start a new island and start competition there. So there is sort of a lot of sort of implicitly, there's a lot of different ecological scenarios within this model, but again, for the most part, we are mostly thinking about sort of the endogenous effects of competition, and again, between individuals and species and across species. And the goal basically is to have a better prior that sort of at least consider a better prior that can consider underneath a lot of other type of modeling that we can inject in sort of where we can have selective effects in it as well as just these neutral effects.
So one of the assumptions was that every new birth is a mutant. Is that right?
No, not that it's what's happening is that there's sort of this there are births and deaths which are just happening, rolling along, And then at a rate which is smaller than 1 on n, 1 on effective population size. So there's a rare rate at which a mutant will arise, and that mutant will contain an ecological innovation. And then hidden underneath all this sort of is what happens, we start with one individual, one mutation after one birth event, and that individual may or may not sweep. But sort of it turns out that once we pass the limit, we only see the ones that sweep because everything else is kind of rare. And so inside of this, for example, I haven't really talked about it, the individuals are still sort of sitting back there in the background. And so what you can have is you can imagine you've got these populations, and they now have effective population sizes determined by what level they're in. They can be accumulating neutral mutations or even weakly selected mutations, because on the scale we're interested in, those don't really have a huge effect. And every once in a while, this is an event that produces a new species. So for example, I didn't really want to make the connection here, but one of the nice things of having an underlying individual-based model is we could just as I've been talking about really the broad properties of the trees that this generate, because that was where we started from, was trying to get trees that looked like real trees. But for example, because this is under individual-based structure lying underneath, we could just equally imagine that we're looking at a neutral marker allele within this population, and then we can see that basically because there can be neutral mutations accumulated with individuals in those lines, and so if we sample an individual from a given level, it's going to have a set of neutral mutations that aren't affecting its level, as well as the crucial mutation that determines its level.
So could you correlate the number of neutral mutations with sweep?
For example,
Sweep
that's the kind of stuff, again, we're in the early stages here, but one of the real goals we'd like to be able to do with this is because we have the sequences of sweeps, partial sweeps, what we'd like to be able to see is, can we look at neutral markers, again, mathematically, and say that that neutral marker is actually carrying this signature because of the sweep patterns of the past. And that's theoretically possible, though, again, still in the early stages, that's work to be done yet.